Here we have a bunch of reactions that alcohols can undergo, and we are supposed to predict the products of these reactions. So here's an alcohol, which is 1, 2, 3, 4. So 2-butanol, which is that, and that is reacting with potassium. Therefore, this is going to deprotonate the hydrogen, as we saw, and produce H2. Okay, so you're going to have that K plus and half H2. Okay, you're producing hydrogen gas and you're producing the corresponding alkoxide. So that's what we saw in the lecture, and same is going to be true whether you have potassium or sodium or lithium or rubidium. Okay, so all the group 1 alkali metal ions are going to give you the alkoxide with the hydrogen as the byproduct, and hydrogen is a gas, so you can either mention that here, or sometimes you will see an upward arrow. That means this is a gas that's going to leave the reaction mixture. Okay, alright, that's the first one. Second one, this is something that I did not discuss in the classroom, but I'm just going to mention it here because it's not a very complicated reaction. So we are again going to have the reaction between an alcohol and a sodium hydride. So let's first look at the alcohol. So you have two methyl groups, a CH, and that CH has an OH, so which means you can clearly see that this is an isopropanol. Right, that's an isopropanol, and you're reacting this with sodium hydride. So sodium hydride should be recognized as the ionic compound. It is. So sodium is going to be a cation, hydrogen being a non-metal is going to be the anion. So sodium metal, hydrogen non-metal, so it's going to be sodium hydride. And sodium hydride is a very basic compound, because hydrogen is a small atom, and it having an extra electron is going to make it extremely basic, because it wants to give the electrons to any acidic species that is in the medium. And here that acidic species is going to be your hydrogen attached to an oxygen, because the oxygen being an electronegative element withdraws electrons away from the hydrogen. Let me make this bond explicit. So if you have an oxygen and you have a hydrogen like that, hydrogen being electropositive compared to oxygen is going to have a partial positive charge. Oxygen is going to have partial negative charge because of this inductive withdrawal of electrons. So the hydride is going to donate electrons to the proton in the alcohol, and the oxygen is going to take electrons from the hydrogen oxygen bond, and therefore you end up making a hydrogen bond, and that means you have H2, and your oxygen is going to now get a full negative charge because it stole the complete electrons in the bond. So oxygen becomes a negatively charged species, and sodium is going to be the counter cation, which is now going to hop from the sodium hydride onto the oxygen. So this is the product. In this case, you are going to get hydrogen gas as well, and you're going to get sodium alkoxide as the main product. Alright, so whenever you have an alcohol reacting with sodium hydride, you're going to get this reaction. The only difference between this and, let's say, reacting the same alcohol with sodium metal, like say for example, if this reaction was alcohol reacting with sodium metal instead of sodium hydride, you're going to get the same product. You're going to get the same product, or products actually, except you're not going to release one full molecule of hydrogen here. You're only going to release half a molecule of hydrogen gas. Okay, and the reason for that is here the sodium is in 0 oxidation state, and here it's in +1 oxidation state. Here we don't have a hydride, here we have a hydride, and therefore two sodium atoms are going to react with two alcohols to give you two alkoxides and one hydrogen, or one alkoxide and half a hydrogen, I mean. Whereas here we have a sodium hydride, and the hydride is going to donate electron to the hydrogen, make it hydrogen gas, and it is going to give you the alkoxide as well. So clearly there is a difference in stoichiometry, but the products are going to be the same, because in one case you have an ionic compound, here you have a neutral metal reacting with the alcohol. So take a look at this, try to understand what's going on. Alright, So this is not a lecture video, so I'm not going to talk about this specific reaction in detail, but this is more than enough for you to know at this point. So for this problem, we have a phenol, and as we know, phenols are much stronger acids than alcohols are, and especially you have something like a chlorine, which makes the ring a slightly electron deficient ring through inductive effect. So parachlorophenol is going to be actually even more acidic than just phenol. So when that reacts with sodium hydroxide, the phenol is going to be a very efficient acid. It's going to protonate the hydroxide, so that becomes H2O. H plus from here, OH minus from here becomes H2O, and therefore sodium is going to become the counter cation for the phenoxide anion you are going to produce. That is that, the sodium cation. So sodium phenoxide is going to be the product, or parachlorosodium phenoxide and water. And this is not going to be a very reversible reaction, because phenols, being stronger acids, can essentially give you a one-sided reaction with a strong base like sodium hydroxide. Now let's look at the thiol here. So we have 1, 2, 3, 4, right? So butene thiol and 2-butene thiol that react in sodium hydroxide. And as we discussed in the classroom again, thiols are also fairly strong acids. Not strong acid like hydrochloric acid or sulfuric acid, but it is stronger than alcohol, is basically what we should know. And that is going to react with sodium hydroxide also to give you a one-sided reaction, which is not going to be in that much of an equilibrium. So the product is going to be SH, alright, and the bisulfide, and you're going to have H2O and sodium cation for the sulfide anion. So the hydrogen here, which I should be calling it a proton, the proton here is going to be picked up by the hydroxide, and therefore sulfur becomes an anion because it is kicking hydrogen as H plus, and sodium is going to be the counter cation over there. And as we discussed again in the classroom, thiols are stronger acids than alcohols. Like, say for example, if we have the corresponding alcohol here, which is then this is going to be a reversible reaction. In fact, the equilibrium more towards the left, because alkoxides are not very stable anions. So this is not a very stable anion. Therefore, water is going to be a stronger acid than the alkoxide, and it will push the equilibrium back towards the left, right? Therefore, this is not going to be a very efficient reaction to produce the anion. Whereas when it's a sulfur anion, which is here, that is very stable, and that makes this a fairly strong acid, and the strong acid being able to protonate protonate sodium hydroxide is going to produce water, right? Therefore, the reverse reaction is not going to be as much of a balancing reaction for this chemical change. And so thiols actually have a pKa that is close to 11. All right, if you look at the pKa for regular alcohols, like for example, let's say this is the alcohol, and we are looking at the pKa for this. The pKa for this alcohol is going to be close to 15, maybe even 16, right? Because pKa for water is 15.7, so this is going to be close to 16 actually, right? Which makes it a much weaker acid. But whereas the pKa for thiols is actually close to that of phenols. So phenols, the pKa is 10, and thiols are going to be around 11. So thiols are much stronger acid than alcohol. Therefore, sodium hydroxide will be able to deprotonate them to produce an anion which is very stable, and there is no significant reverse reaction. And another way to look at this is, if you pick up the acid here, the acid on the left is the thiol. If you look at the reverse reaction, this is the acid which is going to protonate the thiol, and the acid compared to the acid on the left and the acid on the right, the acid on the left is a much stronger acid, because the pK here is 11, the pK for water is 15.5, and this being a much weaker acid will not be able to push the equilibrium to the left. This being a stronger acid is going to push the equilibrium towards the right. Therefore, this is going to be the product and the equilibrium stays to the right. For problem D, we have an alcohol, and that alcohol reacts with sodium hydroxide, and if this undergoes deprotonation, you're going to get the corresponding alkoxide and you're going to get water. Now in this case, you cannot simply leave this reaction as a one-sided reaction. You have to show that this is a reaction in equilibrium, and that equilibrium is pretty much going to be balanced, which means there is no one side that is significantly more stable than the other, right? And that's because, again, by the way, this is a countercation sodium, right? That's because the pK for alcohols is close to 16, and the pK for water, which is acid here, is 15.5, and that's not a significant difference, and therefore this is going to be pretty much a balanced equilibrium. And of course, water is a slightly stronger acid even, which means this equilibrium is going to be slightly more in favor of the reactants than it is towards the product. So this is in contrast to what we just saw for problem E.